Good morning everyone. Thank you for joining me for this video. Let's look over here at this arctan antiderivative. There's a certain integral out there that if you see it, you want to be thinking about arctan as the antiderivative, the outcome of that integral that you would see. When you focus over here, you have an integral which looks something like this, 1 over a squared plus x squared. A could be anything in terms of a coefficient, but when this expression is integrated, you get an arctan come out. And notice how the a's and the x's play out into the antiderivative outcome. You know, this right here is your integral, the integrand, the entire integral. This right here is your antiderivative. And you see the coefficient a comes out as 1 over a, but don't confuse this as the same item coming out here. You have a square here, over here you have a single a, meaning the root of that a will come out here. The x and the a, x and the root of this a. The only reason why I'm saying root over here because the square root of a square is a, so this must be the root of this a over here. A very easy representative of this form you might have seen is anything which would come out looking like this. Then you wouldn't waste time integrating it, you would automatically think of something like that and you'd plug in your answer as arctan, or you can say tan minus 1 inverse tan, and your answer would be just this, plus c. The coefficient here, 1 over a, would disappear simply because a is a 1, 1 over 1 would be just a 1. But the reason why this is the outcome of something like this, you can see that and understand that very quickly by means of trigonometric substitution. When you learn, or if you've learned trigonometric substitution, you will realize when you see something of this form, you're looking at something which looks like a squared plus x squared, and then you're doing certain substitutions. In this case, a is equal to 1 and x is equal to tan theta, and then dx is equal to secant square theta d theta. When you make these relevant substitutions into this form over here, what you end up getting is this. Let's roll it out for you. You have 1 plus tan squared theta. By means of a Pythagorean identity, tan square x plus 1 is equal to secant square x. This right here equals secant square x. You're essentially having secant square theta over secant square theta d theta. These cancel out to give you just this d theta. When you integrate this, you just get theta plus c. But this right here is ambiguous. You have to understand and realize what theta originally was, and you do that by means of this part. If x is equal to tan theta, then theta must be equal to inverse tan of x or arctan of x, and hence you get arctan x plus c, which very well mirrors this form that you're seeing over here. And of course it will mirror this form as you see over here if a were a different value. I want to present 3 examples where the a value changes just so you can understand and commit something like this to memory. That is, if you saw something like this, you can very easily integrate it into an arctan antiderivative, and that will be the purpose of this video. So our 3 examples will go from easy to slightly hard. The only reason why I'm saying this is easy, because if this represents a squared, to determine the root of that is very easy because this right here is a perfect square. What you want to do is when you start looking at something like this, you can say 4 plus x squared is the same thing as x squared plus 4, a squared plus x squared is the same thing as x squared plus a squared. Order does not matter over here. When you see something like this, the first thing you want to start doing is realizing that something like this looks very similar to this. And you want to start thinking about it in those terms. This a squared plus x squared, you want to think about it in that terms. And what you want to do over here is make a substitution. You can always do if u is equal to, and the substitution you want to do is something like this. You'll do x over root of a is what I'll recommend. Your substitution will be something in this template right over here. If u is equal to x over root a, and let's employ something like that over here. So let's do that. U is equal to x over root of 4, which is what, x over 2. And now you'll do derivative of u with respect to derivative of x over 2, which will be 1 over 2 dx, and then dx is equal to 2 du. You know you have to multiply it across. And you'll see why this right here works out for these type of questions. And another thing you want to do is look back over here. If u is equal to x root 4, x is also same thing as root 4u. And let's employ this, and let's employ this into this equation form. Dx has now become 2 du. You have a 4, nothing happens with that. and we know x is equal to root 4u, but you must square it because it's an x square. When you play this out, what do you get? You can bring the 2 out. You have a du over 4 plus 4u square. By doing this type of substitution right over here, in this arrowed area, right here, you end up getting something which is a perfectly easy expression that you can use at Pythagorean identity. Or you can do isolating over here, and you can. You have 2 integral du over 4 parentheses 1 plus u square. Bring the 4 out. Attach it with this 2, you get 2 over 4, which becomes 1 over 2. And integral du over 1 plus u squared. Now we've easily converted this into something which look like this in terms of integral, the antiderivative of this arctan. Your answer over here is going to be 1 over 2. Anything which looks like this will be arctan or inverse tan, arctan u plus c. But what was u? You have to now come back right over here to this form right here. U is equal to x over 2. U is equal to x over 2 right over here. So you present your final answer as 1 over 2 arctan x over root 4 plus c, which you can say in a better way. Root 4 is a 2, right? Root 4 is a 2. You can rewrite this as a 2 over here. So this right here represents the antiderivative of this expression right over here. And you can compare this antiderivative to this. You have a 1 over a, you have an inverse tan, arctan, and then you have an x over a, x over a. Here you're looking at a squares, therefore these a's must be roots of that a square, and this is exactly what you see. Root of a 4 is a 2, root of a 4 is a 2, and you're seeing this over here in terms of the template play out and in terms of the procedure. The most difficult part of this question is not realizing that something like this should bring about an arctan, but it's this substitution right over here, right over here. And then of course understanding that you can do that, and the placement of this value right over here into right over here. When we look at the next two examples, all of this should become more clear. Here is our second example, dx integral 7 plus x squared being in the denominator. It very well mirrors this because we know 7 is a perfect square if that root was root 7. I've placed these two important things right here on the side because these two will play out into the substitution technique. Because we're not going to be doing the trigonometric substitution like how I presented how this technique works out, we're going to be looking at things in this form. If dx over 7 plus x squared, and we know here a squared is equal to 7, a must be equal to root 7. So I'm plugging the things you'll need over here. The first thing we want to do is look at this. U is equal to x over root a. So u is equal to x. X is just x, but over root a, which is root 7. And we can also say x is equal to root 7u. Root 7u. But let's do this in the polynomial substitution technique, then we'll also bring these into play. So if u is equal to x over root 7 du is equal to 1 over root 7 dx, because the derivative of this right here is 1 over root 7, the x goes away. Then dx is equal to root 7 du, and you just have to bring this into play. Dx became root 7 du by bringing the root 7 outside the integral sign. And here in the bottom, when I'm looking at this part right here, I'm substituting this part right over here. And what do I get? I get 7 plus 7x squared. When done properly, these two numbers will be the same because then you can isolate that number and bring in a 1 plus x squared. Let's come right over here. You'll have a root 7 sitting outside. Here you have the du on the top. Here you isolate 7, you have 1 plus x squared. You can bring this 7 outside and hit it with this root 7. You'll have a root 7 divided by 7. Root 7 over a 7 will become a 1 over root 7 because they can cancel out. This is 7 to the 1 over 2, this is 7 to the 1. You can cancel out the exponents and get this result. Here you have a du over 1 plus x squared. Our goal is to eventually come up with this, and then this will easily bring in the arctan, and you know it. Your end result here will be 1 over root 7 arctan or inverse tan, as you see right here. It's the same thing, arctan u plus c. And then here you write the final answer with resubstituting u for what you see right over here. Your answer will be 1 over root 7. I'll just write tan minus 1 x over root 7 plus c, and this right here is my antiderivative, my final answer for this expression right over here. And you see everything play out exactly as a template. 1 over a, 1 over a, x over a, and x over a right here, and then you have the arctan. This video is meant to be short and just for us to understand and be able to implement this where and when needed, because it's an excellent shortcut saving technique. So we should just look at one more example. Here is our question, so let's proceed with it. Dx divided by 8 plus x squared. We know over here a square is represented by 8, so what must be the root of 8? It must be 2 root 2. And this 2 root 2 will play out into these a's that you see right over here, the root a's. So let's start with our first substitution. U over here must be x over root a, right, which is 2 root 2. Because we're looking at the root of a, root of 8. Root of 8 is 2 root 2. X is also equal to 2 root 2 u. What's our substitution? If u is equal to x over 2 root 2, and then derivative of u is equal to 1 over 2 root 2 dx, dx is equal to 2 root 2 du. And we'll bring this right here into place of this dx. I'll bring the 2 root 2 outside the integral sign, then I have a du over 8 plus. What are we going to put over here in terms of x? We'll put exactly what you see right over here. 2 root 2 u square. If you to square this, you know very easily 2 root 2 square is a 4 times root 2 and root 2, and that'll give you your 8. You'll end up having here 8 u square. Remember, the goal end result of all of these substitutions is to have these two numbers look alike so they can be isolated. If you don't have the same numbers popping up here, then your substitution or something here is wrong. You have 2 root 2 du over 8 into 1 plus u square. You can bring the 8 outside, 2 root 2 over 8, and then du over 1 plus u squared. Let's do some simplification of this right here on the side. 2 root 2 over 8 is the same thing as root 2 over 4. But root 2 over 4 can be simplified. You're looking at root 2 over root 2 times root 2 squared. Think about it. Root 2 times root 2 is a 2, but 2 squared is a 4. You can just take one of these and cancel it out with one of these. Because what you really have is a root 2 over root 2 times root 2 times root 2 times root 2. Look, root 2 times root 2 is a 2. 2 times that 2 is a 4. Cancel this out, and what you have a 2 root 2. 2 root 2 ending up coming out 1 over 2 root 2, which is just 1 over a. Or you can just recognize the template and avoid this entire scheme over here on the side, and your answer here, when you do the antiderivative, let's do the antiderivative, will be inverse tan u plus c, but let's substitute u over here so we can do it all here in one single step. U will be exactly x over a, x over 2 root 2 plus c. Let's be a little neat here, 2 root 2 right over here. So this is our answer, 1 over 2 root 2 inverse tan x over 2 root 2. So you see in this video how these type of questions play out, and they should bear enough importance that you remember this template. So your outcome from this video should be such that anytime you see integrals which look like this, you don't have to go through this elaborate process. You should be ideally able to easily arrive at your antiderivative for anything which looks like this. If you saw something which looked like this, 2 plus x squared, your answer should be 1 over root 2 inverse tan minus 1 x over root 2 plus c, because you're able to see the template items play out into this form right over here. If you saw dx over 11 plus x squared, you should be thinking about 1 over root 11 inverse tan or arctan x over root 11 plus c, ideally mimicking what you see here. Dx over, let's say, 20 plus x squared. In this instance, you just have to quickly arrive at the root of 20, which would be 2 root 5. And then your answer would be 1 over 2 root 5. And then inverse tan x over 2 root 5 plus c. So that right there is how quickly you should be able to do these when you see something in this form. And that's the purpose of this video. The 3 examples before just showed you how these forms arise in terms of the substitutions. But that's all the material that I wanted to present for your benefit. I hope you enjoyed this video. Thank you for watching. Have a nice day.